All right, so we're very happy to have the second talk of the afternoon of the second day by Domenico Fiorenza from Sapienza University of Rome, who's going to tell us about string bordism invariants in dimension 3 from U1 valued TQFTs. Please, Domenico.
Thanks a lot, Ishan, for the invitation. Thanks, Urs. Thanks, everyone, for being here. So, what are we going to talk of? So, this is what you're going to see. So, a brief introduction to what is the problem. So, the problem and its solution actually come from a work from Bunke, Neumann, and Redden, but we are going to revisit their construction to see how something that may appear a bit surprising if you are presented just with the solution has actually some story behind it, and this story lies in TQFTs. And then we'll go into the details. So everything I will say here can be made a bit more homotopical, but I will stay really elementary. So I will just talk of morphisms of abelian groups, while a good way of thinking to them, and I'll repeat this over the talk, is that a morphism of abelian group is just a two-term complex concentrated in non-negative degrees. So this should remind you of Dolkan and all that. So if you're familiar with that, please think in that terms whenever you see a morphism of abelian groups. But okay, so time to start. So we start just with an n-dimensional manifold, n is fixed, and we look at its tangent bundle. So its tangent bundle can be seen as a map to BO. So that should be BON, but then we embed ON into ON plus 1, ON plus 2, and so on. We stabilize, and so that TM actually denotes the stable tangent bundle here. And there is a well-known abstraction to lifting this to a stable orientation, which is the first Stiefel-Whitney class, which is a cohomology class in degree 1. And this 1 will have some importance, because if this vanishes, then we can lift from BO to BSO. And now we meet a second abstraction, the second Stiefel-Whitney class. And now this is an abstraction in H2. So you see the degree of the cohomology class has grown up from 1 to 2. And once I have an orientation, I can lift to a spin structure if W2 vanishes, and now the game continues. So the abstraction that I have to go over spin, so to go from spin to string, that's 1/2 P1. That has appeared already yesterday in Arun's talk. And you notice now we have a B4Z. So now the abstraction is in degree 4 cohomology. And then if these vanish, we arrive to string structures, and we can go on. Now there's an abstraction in H8, and so on, and so on. If we kill all the abstraction, then we get to the trivial group, so to a framing. And notice that since the degree of the cohomology class grows and grows, it means that if my n is fixed, above some point, so how does the pointer work? I don't. Okay, above some point, there will be no abstraction. So if my manifold has dimension small enough, after some point, having a string structure will be the same thing as having a framing. There will be absolutely no difference. So a consequence of this is that, in particular, if my dimension is below 7, there is no obstruction in lifting a string structure to a framing. And now if I think of bordism, well, in bordism, there are two dimensions that occur. D, which is, say, the dimension of the manifolds, and D plus 1, which is the dimension of the bordism. So if I think of this D and D plus 1, and I want that to be less than 7, I need the dimension to be below 6. But I will stay well below 6. I will stay with dimension 3. So what I said is that the three-dimensional string bordism group is just the same thing as the three-dimensional framed bordism group. And framed bordism is very well understood by the theorem by Pontiac and Thom. This is just stable homotopy group of spheres. So that is just pi3 of S. So here S is the sphere spectrum, but if you're not familiar with spectra, then just think of that as the limit of the n plus 3 homotopy group of the sphere Sn. And the limit is taken over the suspension maps. And this actually stabilizes quite fast. Already it's P8 of S5. This can be computed explicitly, and it is Z over 24. Let me anticipate that this Z over 24 will come back tomorrow. So what does this sequence of isomorphisms tell us? That if I take a tree-manifold with a string structure, to this tree-manifold with string structure is associated an element in Z over 24. So we may like to realize this element in Z over 24 as some sort of characteristic number. So the ideal would be there is some characteristic class, I integrate it over M, and I get my number. Of course, this cannot work. Cannot work simply because this has to take values in a completely torsion group, which is Z over 24, and there are no torsion subgroups into R. So there is no hope of having such a thing to work. But however, we can think of a variant of this that may work. And a variant that may work is, okay, we do not just use the string structure, we use some additional thing. That in this first slide, I will keep it completely generic. So it's just that Y there. So I take a string structure, I endow it with an additional datum Y. And now, to the pair M with Y, I associate a characteristic class, so some characteristic tree form. And now I can perform this integral. So now, how does the pointer work? No, not this. Oh, here. So now the form depends not just on M, but also on this additional Y. And then I have to take care of what happens when Y changes. So I keep M fixed, I change Y, and if I'm able enough, I can make things in such a way that a change in Y results into a change in the integral by a multiple of 24. So it is not impossible to have an integral that takes just integer values. For instance, any characteristic class does this job. Well, they will be in even degree. Here I need something in degree 3. But there is no a priori obstruction in having this phenomenon of having integrals taking integer values. And then I have to take care of this 24, so I want that when the additional datum changes, the whole integral changes by a multiple of 24. And if I'm able to do this, then I have something that takes values in Z mod 24, well, not for any M, but for those M's that admit the additional datum. So I have to take care of the fact that any M should admit at least one of these gammas. Okay, so this is almost the correct answer. I say almost because here you see the datum is just M, the string manifold, and some additional structure on M, and I just take a tree form on this. I integrate this. So the correct answer is a bit more complicated, but the spirit is the same. So this is M. I endow the tree manifold with some additional structure. So this eta here will be, so M is a string tree manifold, so it has a topological string structure. I have to enhance it to what is called a geometric string structure, which has been introduced by Conrad. But this is not enough. So the additional datum is also a whole 4 manifold. So the additional datum is realizing the string tree manifold as the boundary of 4 spin manifold. And then on the spin manifold, I put a spin connection. And the compatibility will be that this spin connection nabla here should be the same as the part of the datum of the geometric string structure, which is a spin connection. So can we always make this? Yes, because if I look at my spin string tree manifold as a spin tree manifold, then it's an element in the spin three-dimensional bordism, and that bordism group is trivial. So this green 4 manifold always exists. And then there is no obstruction in endowing a spin bundle with a spin connection, and also, as we'll see, there is no obstruction in endowing a topological string structure with a geometric string structure. And here there's the subtlety between what is a geometric string structure that makes everything work and what would be a string connection that is possibly obstructed. So this is one of the reasons why a geometric string structure is defined the way it is defined. Okay, this is just what I said. And now, once I have this additional datum, then I can write my integral. So my integral will have two parts. There will be a 4-dimensional integral, depending on this data here, and a 3-dimensional integral, depending on this data here. And the whole expression is this. So on the green part, so where I have the spin connection, I take 1/2 P1. Since I have a connection, I have a differential form representative for 1/2 P1, which is just a Chern-Weil representative. And then here, on the purple part, this is my tree manifold with geometric string structure. Geometric string structure comes equipped with a canonical tree form. And I can compute this difference. So various things happen here. So this difference takes integral values. And if we change the green part, well, what happens? I have two green parts with the same purple boundary. So I can glue them together, and I have a 4-dimensional spin manifold. And when I compute the difference between these two integrals, this part is in common, so it gets cancelled. And I will get just the integral of 1/2 P1 over a compact spin for manifolds. And by the index theorem, this will be actually a multiple of 24. So this precisely accounts for the fact that a change in the additional structure comes with a change by 24. Okay, so this is a well-defined element mod 24. It goes from string bordism in dimension 3 to Z mod 24. It is clearly additive over disjoint unions. And finally, so this gives the fact that this map is group homomorphism. And finally, I want to show that this is an isomorphism. So to show that this is an isomorphism, one just needs to show that a generator here goes to a generator here. So a generator here is what? So it's a tree manifold, compact tree manifold, with a string structure. But we say that string structure is the same as a framing. So we just have to pick some framed tree manifold. And we have to think of a generator, so the simplest one, S3. And we have to think of a canonical framing on S3. But S3 is just SU2. So as every Lie group, it has a canonical framing, and that is the generator of this group on the left. So everything here is canonical. I can compute that integral. What I get is 1. So generator goes to 1, and this is an iso. Okay, this is completely classical. I have nothing to do with this. It's all due to Bunke-Neumann and independently to Redden. So what I'm trying to explain in this talk is why one should naturally think of a structure of this, why one should came up with this formula, precisely this one, and why is this formula giving integer values. So Okay, so the ingredients. So instead of bordism group, some bordism category. So we want to do TQFTs after all. So I will denote by board with xi, d minus 1, and x. So this is bordism. Objects are in dimension d minus 1. Morphisms are in dimension d. Xi is some tangential structure that for this talk will just be a reduction of the structure group. So for instance, an orientation, a spin structure, a string structure. And x will be a target. So just as in Conrad's talk a few minutes ago, manifolds were equipped with some map to M. And here my manifold will be equipped with a map to X. The difference is that X more generally will be a smooth stack. So if you are not familiar with what a smooth stack is, the prototypical example is, say, the smooth stack of principal G bundles from some Lie group G, or it may be, say, differential form of some fixed degree, closed differential forms. Anything that you can associate with a smooth manifold. So for a smooth manifold M, it makes sense to talk of a map to X, in the sense of it makes sense to talk of a principal bundle over M. It makes sense of talk of a differential form over M, and so on. And what makes it a smooth stack is that this structure can be pulled back along smooth maps. So for instance, Riemannian metrics are not part of this, because you cannot pull back a Riemannian metric along any smooth map while remaining a Riemannian metric, while, for instance, symmetric tensors are. So this is the difference. Okay, so I want to think of this as a category. So d minus 1 manifolds are objects, d manifolds are the morphisms, they are the bordisms. The monoidal product is just disjoint union. And so this is a basic example. I will come back to this several times. So I take as X closed d minus 1 forms. So what is this category? So in this category, objects are oriented d minus 1 manifolds equipped with a d minus 1 form. I'm not saying closed because by dimensional reason that's automatically closed. And what are morphisms? Morphisms are bordisms, so are d-dimensional manifolds oriented, equipped with a closed d-dimensional forms that on the boundary restricts to what I had on the objects. So now what is a TQFT? So for us the domain are these enriched manifolds with these x's and x. And my target is some symmetric monoidal category, and a TQFT with target C is just a monoidal functor, symmetric monoidal functor Z from my bordism category to C. So the typical target is vector spaces. But already this morning in Mission talk, we witnessed an interesting example in which the target were modules for a Boolean semiring. So there are other interesting and easy targets that are not vector spaces. And indeed, in this talk, my target will be the symmetric monoidal category, which is just an abelian group seen as symmetric monoidal category. This has, for instance, shown up in Matthew's talk yesterday. There was some Z acting with a map to C0, and that map was a symmetric monoidal functor. And it was essential in that to look at the group, the abelian group Z, as a symmetric monoidal category. Okay, so I take just an abelian group A, and I denote just by A tensor to stress that I want to think of A as a symmetric monoidal category, just the category which has as objects the elements of A, and which is trivial. They are just identities. So all the associators, unitors, and all that, they are just trivial. Okay, so what is a TQFT with values in A, where A is this one? let us spell it out. Objects have to go to objects. So d-1 manifolds equipped with this map to X and with possibly an orientation or a spin structure or whatever are mapped to element into my abelian group. And then cobordisms have to go to the identity. This means that if I have my manifold M, which is the boundary of W, well, I can think of this as a map from the empty manifold to M. So this will correspond to a morphism from Z of the empty manifold to Z of M. Now the empty manifold is the unit, the functor is monoidal, so it has to go to the unit in A, but the unit in A is the 0 element. So this is a map from 0 to this element. But the only morphisms are the identities. So this condition is that if M is the boundary of W, then Z of M is 0. So this is functoriality, essentially, while monoidality just is that disjoint unions goes to the tensor product into A, so just to the sum. And I have been clicking something well done. Okay. So if you think of these two, then there should be an example immediately coming to your mind that you are surely familiar with, but that maybe you have not yet seen in this light of TQFTs. And it is Stokes' theorem. So we can take as bordism category that bordism category of oriented manifolds equipped with closed form. As target, I just take the additive group of real numbers. And my morphism is just, I take a d-1 manifold with a closed d-1 form, and I take the integral. And Stokes' theorem precisely tells me that this association is a TQFT with this target category. So, other examples. So, I can consider, say, an SO bundle with a connection. And if I take the Chern-Weil representatives for Pontryagin classes, these are morphisms from SO bundle with connections to closed forms. But now I've seen that if I start with this bordism, so bordism with closed forms, then I have this TQFT with values in R. And then I can do this composition, and I get a TQFT which starts with manifolds equipped with principal SO bundles with connections and gives real numbers. What is this? Is just the characteristic number. And as everyone knows, the characteristic number does not see the connection. So this factors down to a theory that starts from here. And finally, if I take a manifold, I can take the tangent bundle. That is a section of to the forgetful morphism. And so in the end, I get a theory that starts just from 4k plus 1 dimensional bordism oriented and goes to R. And what is this? I take a manifold and I take the integral of some characteristic number. So all this summarizes the fact that these are cobordism invariants. So a classical theorem about cobordism. And what here I did with a single class, of course, can be done with any polynomial in Pontryagin classes. And actually, every cobordism invariant with real values is obtained this way. So in a sense, every cobordism invariant with real values come from a TQFT with this funny target, which is just real numbers with their additive structure. Okay, but we have to introduce something more. So something more is not using just a single abelian group, but considering a morphism of abelian group. Or, as I said before, you can think of this as a two-term complex. So you have one group, which is the group of objects. This is the one that is in degree 0 in the complex. And then you have a group of morphisms. So this one, which is in degree 1 in this chain complex. And the way this group is seen as morphisms, well, this is just Dolcan correspondence. So morphisms from A to B are those elements X in the group of morphisms that move A into B. And okay, so it's very simple to see that the addition here and here endows all these with a symmetric monodal structure, and so I can take this as the target for my TQFT. So let's see some examples of this. So what will be the general structure? So something like this. But now the object M will go to an object, and now a morphism, say a bordism from the empty set to M, will go to a morphism, but this morphism will not necessarily be the identity. It will be some object in the space of morphisms. So it means that here I do not have 0, but I have that this, say, minus 0, is the image phi of some, say, V, with V an element in the group of morphisms. So now minus 0 disappears. So the kind of equations you have to witness is the fact that whenever your manifold M is a boundary, then the value on M is computed via something which is associated actually to the bounding manifold. And also of this, you have seen several examples, but hopefully for me not in this slide. So Stokes' theorem, but now without any restriction on the forms to be closed. So in this case, I have just d-1 forms. So a d-1 manifold goes to the integral of the form, and a D manifold goes to the integral of the de Rham differential of that form. And Stokes' theorem tells us that if, oh, no, sorry, I have to remain on this. So if I have my manifold M, which is the boundary of W, then this formula is precisely the fact that the integral over M of something is just as the integral over W of the differential of that form. So here the morphism is just the identity of R. So another example where I do not take the identity. So let me take principal U1 bundles with connections. And as morphisms, I take the exponential from R to U1. So this means now that objects are elements in U1 and morphisms are elements into R. So my object will be one manifold together with a principal U1 bundle with connection, and associate to them the holonomy of the connection. And my morphism will be two manifolds, again with a U1 bundle with connection, and I want to associate to this a real number. And I associate the integral of the curvature. And now the relation between holonomy and curvature, in the case where my one manifold is the boundary of a two manifold, is precisely this formula here. And this formula here is precisely the fact that when my manifold is a boundary, the value of my TQFT on the manifold is the image through this map of the value on the bounding two manifold. So these are all examples of this, and this can be done in higher degrees, but let me skip this. Okay, now I'm moving towards spin and string. So this is the topological situation here. So I can consider the classifying stack of spin bundles. In the first slide, we had the classifying space of spin bundles, and these are a map to KZ4, but this can be refined to a morphism of smooth stacks from B spin to B3 U1. This is the tree stack that classifies U1 two gerbs. And this is due to Brzezinski and McLaughlin at the level of cocycles. They provide this map, and then with Urs and Jim Sashev, we gave an interpretation in terms of stacks. And also, Brzezinski and McLaughlin show that all these leads to the case of connections. And what will be relevant to us is that if I start from here, I take the curvature, this will be a closed form, and this closed form is nothing but a Chern-Weil representative for 1/P1. Okay, so if I start now with target spin bundles with connection, and I consider oriented tree manifold with values here. So from spin bundles with connections, I can go to this symmetric model category here, and the maps are the following. So I take my spin bundle, I consider the associated U1 tree bundle, and then I take the holonomy on the tree manifold, and on the bounding 4 manifold, I take the integral of the first fraction Pontryagin class. And these two are related exactly as holonomy and curvature for U1 bundles. So this is an example of a TQFT with this source and this target, and I will call this Z spin. This is our first ingredient. And the second ingredient, as you see we are going here, will be geometric string structures. So I said this is the topological part, this is the part with connection, and the part with connection in a 3 U1 bundle will have a topological datum that will be transition functions, but then will be also a 1-form part of the connection, a 2-form part, and a 3-form part. And we can forget step by step the 3-form part, then the 2-form part, and then also the 1-form part, and remain just with the transition function. So we have a sequence of forgetful morphisms here, and we also have this Pontryagin class from spin bundles with connection to the first element in the series here, and composing with some of these forgetful maps, we have this sort of refined Pontryagin classes which are more or less refined. So the higher the index I is, the more refined it is, the more I retain of the connection data. And we are interested in the case I equal 2. So for any I, we can form this pullback, and this we will call string bundles with partial connections. And the case we are interested in is not I equal 3, that will be a full-fledged string connection, at least one of the possible definitions of what a string connection would be, but we will be interested with the case I equal 2, which is what is called a geometric string structure. And the reason for this will be clear not only for this talk, but especially in this terminology, geometric. So geometric wants to be close to topological. So we want to see that when I is 2, there is no obstruction in going from B string, just a topological setting, to this geometric setting. While we will see that there is one obstruction to going to a, well, I'll be more precise later on what is the obstruction. Okay, so how can I think of this 2 case? So in the 2 case, I start from here. I forget most of the, I keep all of the connection data, and then I forget part of it. What I forget is precisely the tree form part. So I can split this big pullback diagram into 2 pullback diagrams. So here is what remains when I forget the 3-part connection. And then I can read at this part as a pullback diagram. This means that a geometric string structure is a spin structure with connection together with not a trivialization of the whole tree bundle with connection, but only of the lower part. So there is a remaining tree form. This is precisely the canonical tree form of the geometric string structure. And if you remember the first part of this talk, I was needing a canonical tree form on my tree manifold. And it will be precisely this one, this omega tree. And so if I merge together all the diagrams I had before, I get this diagram here. And this tells me that this canonical tree form is actually a trivialization of the first Pontryagin class. So the differential of omega 3 is 1/2 P1. And this is the crucial equation that will make the difference between those 2 integrals to be an integer. Because on the 3 manifold, we are integrating omega 3. On the 4 manifold, we are integrating this part here, and these 2 are related by this equation. So why geometric? So if you look at what are the obstructions in going from topological to geometric, you meet 2 of them. And these 2 are in H2 of omega 1 and in H1 of omega 2. But for a smooth manifold, differential form are a partition of units, so these higher cohomologies are 0. So there are no obstruction in going from topological to geometric. If we want to go up to I equal 3, then here we get H0 of omega 3. So we have a tree form that represents the obstruction to lifting a given geometric string structure to a full-fledged string connection. Here, one has to pay attention. This is just telling me that that specific geometric structure may not lift to a connection. It does not tell me that the original topological structure does not lift. I could have a different choice of a geometric structure, and that may lift. This is a subtle analytic question. I don't know the answer of this. So, but this is to be thought as open, I think, at the moment. Okay. So, summarizing, geometric string structure are topological in the sense that principal spin bundle can be enhanced to a geometric string structure if and only if its first fraction Pontryagin class vanishes. Okay, now we can go towards the conclusion. So far we have constructed symmetric monodal categories associated to morphisms of abelian groups. And as I told you, I have to think of this as a complex. And now I can take 2 of these complexes, and there is a natural notion of morphism between them. It is just a commutative diagram like this. So I will have a symmetric monodal category here, a symmetric monodal category here, and it is very simple to see that these morphisms here induces a symmetric monodal functor. And when I am in this situation, so I have 2 symmetric monodal categories and a symmetric monodal functor, I can take the homotopy fiber of this to get a 3rd symmetric monodal category. So what is that? Well, objects are just object in the source, say X, together with a morphism from C. C will always be the unit object in the target, from the unit object to the image of X. And morphisms will be morphism in the source, so some A from x to x prime, such that this diagram commute. And this will in turn have a natural structure of symmetric monoidal category. So I can take these homotopy fibers as targets. And okay, this is just what I said. And so what is that is that in this simple example, the homotopy fiber has a very explicit expression. So I can say both what are the objects and what are the morphisms. So objects, so we have this diagram, and objects are just objects here in H, morphisms in G, that are the same here. So it's just this fiber product. And also morphisms are very explicit. So morphisms are morphisms between pairs, and so they are the morphisms here that are morphisms both for the G's and for the H's. So everything completely explicit, but there's some good news. So assume you have a splitting of this diagram this way. So then things become much nicer. So we have a natural map from the homotopy fiber of F is the big diagram, to just the kernel of the bottom map here. And moreover, if the top map here is an iso, then this map is an equivalence. So this can be shown either completely explicitly using the formulas I had on the slide before, or more nicely thinking of that this is a chain complex, this is a chain complex, and then it is natural to think of a map going backwards like this. This is just a homotopy between the chain map that you have here and 0. So you are just saying that if your morphism of chain complexes is null homotopic, something nice happens. And so whenever you have a null homotopic map between chain complexes, the homotopy fiber is just the direct sum of one of the complex with the truncation of the other. Here you see the truncation of the other. And if the map on the top is an iso, it means that this complex here is acyclic, and then you don't see it at all. So you just see this. So no surprise in this, but it's useful. So it's useful because now we can put everything together and get our formula. So remember that starting with geometric string structures, we add this canonical map to 3 forms. So taking bordism, we go from bordism with target geometric string structure to bordism with target 3 forms. And we already noticed that out of bordism with target 3 forms, if my bordism is in dimension 3, we have a map with target the identity of real numbers. This was Stokes' theorem, the second part, and the first part is just this canonical morphism here. So we get TQFT that starts from here and ends here, which I will call Z string. And remember that we also had a theory which I had called Z spin that was starting from the analog of this, but with spin connections, and was ending up into exponential of 2pi. So let me be more explicit here. What is Z string? On a 3-manifold with geometric string structure, I pick up the canonical 3 form of the geometric string structure, and I integrate it. And what is on a bounding 4-manifold? Well, the rule is dictated by this second part of the diagram, so I have to take the integral over W4 of the de Rham differential of this. But I recalled before that the de Rham differential of this is just 1/2 P1. So I can say that on W4, I take 1/2 P1. We'll have to remember this in a minute. So we have this, and then we have this commutative diagram of groups. this is the most trivial one. Identity here, exponential, exponential. And so this will induce a symmetric monodal functor from identity here to the exponential. And this also clearly will split, because here I just put the identity. And this will be splitting this diagram. So I have the Z string, the Z spin, the forgetful morphism that forgets the string part going just to the spin. And here I have that commutative diagram giving these morphisms of symmetric monodal categories here. And this commutes. So I have a commutative diagram here, and if I have a commutative diagram, this will induce a morphism between the homotopy fiber on the left to the homotopy fiber on the right. Just abstract nonsense. I have morphism between two things. I take fibers over the same point, and fiber goes to fiber. But now, as I said, the diagram, this diagram, has a very simple splitting given by the identity here. So the homotopy fiber of this has a quite explicit description. It's just the kernel of the map on the bottom. And the kernel of the bottom map is just Z. So this a theory which has as a target the homotopy fiber of this is just a theory which has as a target integers. And also, the isomorphism here is completely explicit. On objects, it's just given by the difference. Okay, so we put everything together. We have a canonical morphism from the homotopy fiber of this to the integers. And the claim is that this canonical morphism is just the morphism from the introduction. And why is this true? Well, let us see what an object here is. So, wait, no, I have to draw it. Or better, well, I draw it better. So, what is an object in the homotopy fiber on the left? So it will have to be an object here. So this M will be a spin manifold. Will be an object here. So M will be a string manifold. And then there will be a morphism in the target between the unit object of the target and the image in the target of this. So the target is spin. So it means that I have to take M as a string manifold. I have to forget the string structure and retain only the spin structure. Now this has become a spin manifold. And I'm looking at a morphism between the unit object in spin bordism from the empty set to this into the category of spin manifolds. So this W has to be spin. So objects in this homotopy fiber here are precisely string manifolds together with spin bordisms. And then with all the additional data. So here there is a spin connection, here there is a geometric string structure. And if you work out what this morphism is, this is precisely the formula in the introduction. Notice that the minus sign in that formula in the introduction is this minus sign, the canonical minus sign that we get here. So, two very quick concluding remarks. So, everything here was based on 1/2 P1. One can play exactly the same game using the first chunk class. And in this case, one would get something that has not 1/24, but as 1/2. So the 1/24 was the one over 24 that appears in the A hat genus. So this will be the 1 over 2 that appears in the Todd genus. And everything is completely the same. The role of the index theorem there is the fact that for two-dimensional closed complex manifold, the integral of the Euler characteristic is even. And something which is more interesting is, okay, can I get z over 24z going one step higher in the weighted tower of the orthogonal group? So if I use 1,6p2 and I use 5 brane in place of string. So if I work with something that should be a geometric 5 brane structure. Well, the answer here is I don't know. So everything works fine. The factor 1 over 24 appears correctly in the A genus. Actually, all the image of the J invariant appears as coefficients in the A genus. This is very classical, it's due to Adams. So on that side, there is no problem at all. The real problem is that you see the construction. Here you use actual connections on spin. So in order to mimic this one level higher, you will need to have an actual string connection. So if every topological string structure can be enhanced to a string connection, then the game can be played. But this is presently not clear to me. So this actually is a problem just in analysis, so maybe someone in the audience already knows the answer, but I do not know it. And let me conclude with a question to you instead of receiving a question myself. So what change? So if I fix one spin connection, then I can lift to a geometric string structure. And now I have my omega tree. This omega tree is the obstruction to lifting this to a string connection. Okay, but my datum was completely topological. This is some choice I made. So I could start with another spin connection and hope that this time this vanishes. But if I change this with nabla prime, well, then nabla prime is nabla plus omega, with omega, which is a one form with values in SO. And the difference here, omega 3 prime, will just be omega 3 plus Chern-Simons of omega. So the question is, can I change by a Chern-Simons term in order to get 0? The question then is, it is true that if I consider this map, I take one form with values in the Lie algebra G, and I take the Chern-Simons. Is this surjective? Or it is at least surjective modulo exact tree form. This would be enough. I do not know the answer to this question. So if any one of you knows, Dan knows?
Sullivan proved that if you stabilize.
Sorry?
I think Simons and Sullivan proved that, so if you stabilize your vector bundle by trivial bundle, then the answer is yes.
Ah, great. Then we are going to talk of this on the Safari.
Okay, great. Thank you. Okay, I think we have enough material to discuss in the Safari. Any quick questions for Domenico? Okay, let's thank him again. Thank you. Thank you.